presentation, we want to give the food testing scientist an overview of the QTRAP technology and review some of its relevant functions that will specifically benefit the workflows that are applied in routine food testing lab. In addition, some details of how those functions can overall improve the general workflow in a food lab, and some results will also be discussed here during this presentation. As you know, in general, routine LC-MS analysis involves many steps, including chromatography. Chromatography separation of your analytes of interest from each other, but also from the matrix and from the interferences. This is very important for detection of the analyte of interest. Production of the ions in the gas phase is also very important, using one of the typical LC-MS ionization techniques. This will, of course, depend on the nature of the analytes of your interest. Since most of the contaminants screened for in food labs are relatively ionic and polar compounds, electrospray ionization technique has been the most widely used in the labs. And once those ions are formed in the gas phase, they will be filtered by one of the mass analysis according to their mass to charge ratio. In screening mode, we generally use multiple reaction monitoring method and sometimes followed by a triggered MS scan for identification. This is a typical workflow using the QTRAP LC-MS system from AB-SCIEX. Then detection of the ions formed, and then the data analysis, which is by far the most important part of any LC-MS analysis. Either qualitative to know what you have found in the sample analyzed, and most of the time you also want to quantify what you have found and what you have confirmed using the QTRAP technology. So here some examples are shown in this slide. The goal is to go from a real live sample to a relatively complicated chromatogram and be able to identify and quantify your finding with high reliability. The key overall question for routine testing lab is what is in my sample, and if there is any, how much of it is there. Let's consider an example of the food testing lab shown here in red arrow. So the average food testing workflow involves in general 6 steps processes, and many questions could arise during each step of these processes. Sample must first be extracted to collect the residue of interest. Then samples are often cleaned up to remove the unwanted matrix interferences. Then the sample is injected into an LC system, and the residue are separated for an ideal detection. Then the residue are detected. In this case, in LC-MS, we use the mass spectrometry detector. Then once you have the data, you need to find the best way to process the data and to identify any residue detected in your sample. And then, of course, most of the time, we want to quantify how much of those residues are found in there. So once again, the key overall question for routine testing lab is what is in there in the sample and how much of it is there. For everyone that is doing or has done food testing is aware of that there are many questions that can arise at each step of the processes. This is including understanding the composition of the matrix to ensure proper extraction and cleanup, the hardware optimization to ensure excellent peak shape and sensitivity in both the LC separation and mass spec analysis. When it comes to data processing, labs always want to be sure that their results are accurate, and they have a good limit of quantification to meet any regulatory demands. All these questions you see here in this slide need to have some answers to ensure accuracy of the result. Using AB-SCIEX QTRAP system can help you to address many of these questions or concerns that routine testing labs are facing during the everyday work. This is because the QTRAP system is not just an ordinary triple quadruple mass spectrometer. The QTRAP system goes beyond basic MRM detection to help resolve many of these questions by producing results with much better sensitivity and selectivity and providing more data to help resolve matrix interferences from compound of interest and overall to provide better confidence to ensure that the reported results are the right one and very close to the truth. So as I have just mentioned, using the QTRAP technology, you could go beyond just basic MRM detection to help you resolve many of these questions. This is mainly using two unique QTRAP functionality, including Enhanced Product Ion Scan mode, or EPI, and MRM³ scan mode, which I will be discussing each one of them separately in more details in the following slides. First, a little background on the QTRAP technology and what makes a QTRAP different from a triple quadruple system. The fundamental difference is the linear ion trap. In a QTRAP system, the quadruple Q3 is able to function as a regular mass filter, but also able to function as a QTRAP, as a trap. Therefore, the QTRAP system is able to do regular MRM function and could also trap, dissociate, and accumulate the fragment to do a fast and high-sensitive full scan experiment. This includes, as I said before, the Enhanced Product Ion Scanning, or EPI. Whether the AB-SCIEX QTRAP system used is a 3200 or 4000 system, having a linear ion trap or a curved ion trap in the QTRAP 4500, 5500, and 6500 system, the principle of the QTRAP functionalities is very similar in all AB-SCIEX QTRAP systems. When Q3 is used as a normal quadruple mass analysis, the QTRAP system is able to be used as a regular triple quadruple system and could also be used to do regular MRM function. In this case, the parent ion is selected in first quadruple Q1, dissociated in the collision cell Q2, and then particular daughter fragment is selected in Q3 and detected. In this case, both Q1 and Q3 are continuously scanning looking for parent fragment pair. The result of that will detect one MRM or parent-daughter pair of interest, which you typically pre-select. When you turn the Q3 into a linear ion trap, all the product ions are collected in Q3 for a given time, called fill time, and then scanned out. In this case, all fragments associated with that pre-selected parent compound are detected, giving you a full MS-MS profile of the parent ion. This MS-MS spectrum represents a specific and most of the time a unique fingerprint of the analyte detected. Using QTRAP system, this is typically called an EPI spectrum that is going to be used for a library search to confirm the identity of the parent ion. The EPI spectrum provides an improved MS-MS sensitivity and can help to decomplicate results that may be implicated by matrix effect. In addition, it can give you an extra sense of confidence in feeling that your results are the right one. This is with no extra time and no extra work is required. In addition, there is no re-injection. One injection is enough for everything. Let's go into more details and show you how this EPI spectra could help you to give you more confidence into your analysis. The overall screening and confirmation strategy for routine analysis is as follows. We use a survey scan using a list of MRM, and every time there is a peak above certain threshold, an EPI spectrum is collected and used for library search, identification, and confirmation. This is practically using what we call MRM IDA triggered EPI method. And here is an example showing really how is it done. A list of compounds to screen for could be 100 of them, and every time there is a peak that is detected, it will automatically trigger an EPI spectra that is going to be used for library search, identification, and confirmation. So if we go back to the questions around the food testing workflow, let's start with the question around sensitivity. Most of the food labs always question if they have the right sensitivity to detect the concentration level they need to meet regulatory limits. Or perhaps you are concerned that matrix suppression, which is very common in food samples, is reducing your sensitivity and jeopardizing your ability to accurately quantify residue to the limits you require. By using EPI scanning, you would certainly get much more sensitive data than you would generally get using just a regular triple quadruple system. Since the fragments are trapped and accumulated in Q3, this can give you a boost in sensitivity of your product ions. EPI spectra could be as high as 100 times more sensitive than a regular MRM spectra using a traditional triple quadruple system. This could be very useful for confirmation of low traces of contaminants in food samples. Here is an example. An MRM is detected and an EPI scan was triggered. The result being that all fragments, including the one that was initially detected, are measured and compared to an MS compound library. Each fragment with sufficient sensitivity to enable accurate library comparison and get you more confidence into the confirmation of your analyte. However, when the same product ion is done using a triple quadruple system, the sensitivity is much lower. The result could be poorer. MRM ratio may also not be, detected. The second MRM might not even be detected, making quantitation with confirmation a challenge. By having the sensitive full scan MS data using the QTRAP system, the library fitting can help you in enabling the confirmation of this residue even at very low levels. Here is another example showing you the sensitivity of an EPI scan with QTRAP, and that's using a regular product ion scan with a conventional triple quadruple mass spectrometer. The sensitivity of all fragments detected using QTRAP makes confirmation better and more reliable. 3 additional fragments here in red are much better visible in the EPI spectrum using the QTRAP than in the MS spectrum using regular triple quadruple system here shown in this slide. Every lab and every scientist wants to feel more confident about the result that they have or they are reporting that are the right one. Using the QTRAP can add to that confidence. The biggest question of all is, am I sure of this result? How confident I am to report this result as a positive finding? The EPI scan using QTRAP can provide more information about your peak beyond just the retention time and the MRM ratio. Using all of the MS-MS fragments and comparing that MS-MS fragmentation pattern to library spectra, you have another checkpoint to use to confirm your positive finding and to feel more confident about reporting your results. So let's examine this first example. The MRM ratio of the imazalil standard is about 0.6, and the retention time is 9.1 minutes. The food sample in the chromatogram underneath shows an extract, shows 2 colutin peaks with an MRM retention time with an MRM ratio of about 0.5, which is within the acceptable range. The retention time is about 9.3, a slight shift of the retention time, which is generally very normal in the food matrices. Overall, a good match between the standard and the food sample peak. And the question is, how sure are you reporting this as a positive finding? Using an automatic triggered EPI spectrum could give you a more confidence of reporting this result. In this case, the spectrum of the unknown peak matched the library spectrum of imazalil with a fit of 90%, of more than 90%. So although the MRM ratio was slightly off and the retention time was a bit off, making the result a little ambiguous, the EPA scan data could be useful to decomplicate the result and can give you more confidence in reporting this as a positive result. When matrix effect caused this ambiguity in the MRM ratio, collected on an ordinary triple quadruple mass spectrometer using QTRAP EPI scanning and the full MS-MS fingerprint of that peak can be very beneficial to overcome this and be more confident of reporting your results. Here is another example. In this case, thiobendazole was detected at a reasonably high concentration in food sample. MRM ratio is within the acceptable range identified by the standard, and the retention time is slightly off. You can use the QTRAP with EPI triggered spectrum to verify this result and give that extra sense of confidence. Again, the same question, how sure am I or are you to report this as a positive finding? The full MS-MS spectrum acquired from using the EPI scan and using the QTRAP matched the library spectrum for thiobendazole with about 93% of feed score. In this case, the EPI data was used to confirm the positive findings so that you can feel more secure that you are reporting the right result. In this case, example number 3, metalaxyl was detected in the food sample. The MRM ratio is within the correct acceptable range determined by the metalaxyl standard, but the retention time is slightly off. And again, as I mentioned earlier, shifts in retention time are not so unusual in food sample due to the matrix effect on the analysis. You might not be totally sure if you should report this as a positive finding or not. Again, the MRM ratio is a very good match. Now, by using the QTRAP system and the EPI scan, this would have triggered by using really the QTRAP system on the unknown MRM peak in the food sample. A full MS-MS spectrum of that peak will help you really to identify and to actually make sure that and avoid reporting a false positive for the result. The full MS-MS spectral data help to verify the result, particularly when MRM ratio and retention time results are a little ambiguous. This is very clear to show that although MRM ratio and the retention times are a very good match, the EPI spectra help you avoiding the false positive of this result. Here is another example with very similar scenario. Very good match of the MRM ratio and the retention time. And again, the same question, how sure are you of reporting this as a positive finding? And once again, the EPI spectra could help you avoiding false positives. Again, you could see here very clearly, although the MRM ratios are in very good match and the retention time are really in good match, the EPI spectra would help you to avoiding this false positive. One last example here where we have a perfect match of the detected peak at 1.7 minutes in the food sample. And the MRM ratio is also in good matching. From the perspective of a lab technician, this is a definite positive hit for omitoet. But if we examine the EPI spectra detected or collected by the QTRAP system, you can always still guess and wonder how sure you are. And again, once again, the EPI spectra could help you avoiding the false positive. When the EPI scan was triggered on this peak, the full MS-MS spectrum was compared to a library spectrum for omitoet. The resultant library match showed only a 26% of fit score. This result tells us that this peak was not in fact omitoet, but was simply an interference. Had we simply used the retention time and MRM ratio, this sample and the previous samples would have been reported falsely as a positive finding. Just this one another example of how EPI data using the QTRAP system can help you to ensure that the right results are reported. As you have seen from the last three examples, the EPI spectra could help you avoiding false positives. This is because MS-MS fragmentation patterns provide a unique chemical fingerprint and avoids reporting false positives. Let's examine here, let's go into more details and examine and show you how the second unique function of the QTRAP, MRM³, could help you or could give you more confidence into your analysis, especially in the food testing labs. MRM³ offers a high level of selectivity beyond standard MRM. It could help to overcome matrix interferences and also with potential to improve the signal to noise and ultimately provide a better sensitivity. In EPI mode, the linear ion trap or Q3 function in trapping mode and trapping all the fragment ion and slowly scanning them out, allowing for high sensitive detection of product ions. But the linear ion trap can also function as a second collision cell to dissociate any trapped fragments, allowing for the detection of secondary fragments of the primary fragment. This takes MRM one step further into MRM³. When performing an MRM³ experiment in a QTRAP system, the first precursor ion or the parent ion is selected using the first quadrupole, Q1, fragmented into the collision cell, introduced into the collision cell and fragmented, and all product ions are trapped in the linear ion trap. Then the second precursor ion, which is generally one fragment ion, is isolated and fragmented in the linear ion trap. Finally, the second generation of product ions is scanned toward the detector. With this extra isolation and fragmentation step, MRM cube is more selective than the traditional MRM mode. It can be useful for quantification in this case, especially in the cases of high noise background and interferences. The principle is very similar in the curve ion path QTRAP system, especially in the 45, 55, and QTRAP 6500. For food testing labs, MRM³ could have some workflow advantages, particularly when addressing matrix interferences. Even with the selectivity of MRM mode, food matrices can create high background peaks. MRM³ adds an additional dimension of selectivity to potentially remove some of those interferences. It should also be noted that adding that extra dimension of selectivity by measuring parent, daughter, and granddaughter MRMs cube transitions, signal to noise for your peaks may also be improved. So, enhancing sensitivity as well as improving selectivity. So here is an example showing the significantly improved selectivity for detection using MRM³. In here, the elimination of chromatographic interference and background noise is very visible, which will improve the limit of quantification of the detected peak. Here is another example where there is a matrix interference peak that is nearly coeluting with the compound of interest. When using MRM³, that coeluting peak is eliminated, providing a better result, especially for residue food and for quantification. In this example, MRM³ was used as well. The first MRM transition shows many peaks, and the second MRM transition is not even visible and is not very sensitive. When using MRM³, the background interferences from the matrix are eliminated, and a well-resolved peak emerges. Also, it is clear that sensitivity is improved. With this added selectivity, with the signal-to-noise ratio improving from 10.3, as you could see in the slide, to the parent-daughter MRM to 22.6 for the parent-daughter-granddaughter MRM³, this allows you really to improve a limit of quantification for the detected peak. From this example, you can see the potential for MRM³ to not only eliminate background peaks and interferences that occur due to the matrix, but also the potential to improve sensitivity for low-level residue scanning and quantification. And this is very important in food residue analysis. In summary, this presentation gives an overview of the two unique functions of the QTRAP technology that can enhance and improve routine contaminant testing workflows. With EPI scan, you are able to enhance your routine MRM detection by adding the extra trigger MS-MS to detect all fragments. The result is better sensitivity for MS-MS spectra and less false positive results due to the ability to match a full MS-MS spectra with library spectra for added confirmation and identification. With MRM³, the added dimension of selectivity not only enables labs to overcome matrix interferences that may be causing background peaks in their MRM chromatogram, but to also potentially improve their sensitivity for more accurate level of quantification. And both of these functions can be easily added into routine screening and quantification methods. Once the method is setting up the EPI method can take really less than 5 minutes. No extra time or extra work is required. QTRAP function can help enhancing routine contaminant testing workflow. This is by increasing confidence in compound identification and increasing selectivity for quantification of your finding. To learn more about the QTRAP application for food testing application and to see some videos showing you how to implement these workflows and the QTRAP functionalities in your own lab, please visit our website www.abscience.com/QTRAP for food testing.